Hello everyone, my name is Alex Dahl. I'm a mineral grinding specialist, and in today's video we're going to talk about conducting a SAG mill ball mill circuit plant survey. So what is a SAG mill ball mill plant survey? It's going to be a health check for your grinding circuit. Ideally, treat this the same way you would treat your annual checkup visit to the doctor. It should be performed periodically, whether you think you need it or not. Typically in a plant, you should be doing one about every year or maybe twice a year, depending on how often the ore types are changing and how much variability you expect to see in your circuit. You want to make sure that when you conduct the survey, the plant is running smoothly, so you shouldn't have pump boxes overflowing. You shouldn't have the SAG mill speed ramping up and down as the expert system is doing whatever expert systems are doing. You want to make sure that your instrument calibration is all up to date so that the feed belt weightometer on the plant feed belt, that should be as accurate as you can get it. You want to make sure that things like the flow meters and the density gauges around the cyclone circuit, those are all tuned up and giving you, the best data that you can get. You want to make sure that there's a consistent ore feed available. You don't want to have the ore characteristics changing halfway through the survey. And you also want to make sure that you have enough labor available. So you got people are not rushed. You want to make sure that there's enough people who understand how to properly take a sample in a particular situation. And you don't want to have people racing all over the mill. For example, racing from the cyclone overflow down to the ball mill to then take a sample at the ball mill. Have people stationed at the ball mill, have people stationed at the cyclone. Make sure that people are not rushed. Objectives. We're trying to measure the specific energy consumption in these circuits. So you're looking at things like the specific energy consumption, kilowatt hours per ton. In order to do that, you need to generate data from the control system. That's your PI data or data historian. You're looking for power draws, you're looking for dry tonnages. One of the metrics we're going to use is functional performance. So this is a framework that was developed by Rob McIver and Metcom Technologies, and it measures specifically performance around the ball mill circuit. We're going to be looking at the power draw in the mills. I'm not going to deep dive too much into this. That could be a separate video. So the plant survey. Before you do the survey, you need to very carefully identify what your sampling points are going to be. For example, the plant feed, you're going to basically take the feed that comes into the SAG mill, and that's going to have to be a conveyor belt cut sample. So you identify where on that conveyor belt you can safely access it, where you can get the barrels in to collect the sample, where you're going to perform the lockout to make sure it's safe to operate. And make sure that this is the fresh feed and that you don't have the crushed pebbles on that belt. Right? You're trying to get the fresh feed that's coming in from the mine and not some recycle stream blended with that. You're going to want cyclone overflow and underflow. Those are very important. You're going to need the ball mill discharge. This is an important one especially for functional performance. And if you have something like a discharge trommel where you don't have like a nice collection point for that slurry, you might need to get your mechanical people to arrange for some sort of a sampler that can pass underneath the trommel and representatively sample everything that's passing through the trommel along the length of it. If you can get a SAG mill product or a SAG screen undersize, definitely do get that. The pebble streams, both before and after a pebble crusher, those are helpful. They're not mandatory, but they are helpful. Cyclone feed, it's helpful if you can get it. Not all plants are able to get that sample. But the more redundancy you can build into the sampling, the more robust your mass balance is going to be, and the more robust the results of the survey are going to be. The GMG group, the Global Mining Guidelines group, they have a guideline specifically for sampling grinding circuits. So I'll put a a link in the description that you can go and fetch that guideline and use that to help you inform how to go about doing things like collecting the samples safely and how to keep them representative. There's a bunch of issues in the guideline related to the geometry of samplers, very important. So yeah, grab that guideline, it's free, everybody can use it. So the specific energy consumption is a measurement of the kilowatt hours per ton required to grind your ore. And what we're going to do with this metric is we're going to compare a laboratory measurement to what you observe in the plant. So you're benchmarking your plant against the laboratory. You're going to be using generic measurements and generic models like the Bond model, the Morel model. You can use Barrett's recalibration of the Bond model for SAG milling. And these benchmarks will tell you whether or not your operation is consuming more energy or less energy than what these metrics predict that you should. And ideally, the way that these models were generated is that the authors of them, like Derek Barrett and Steve Morel, they collected a bunch of data from around the world, and they found how should a typical plant operate given a particular ore hardness. So if your plant is consuming more energy than what these models predict, that's a sign that there's something is operating inefficiently, consuming a lot more energy than what these models are predicting. Functional performance, I mentioned this, it's broken into two efficiencies. So the classification system efficiency, this tells you how well your grinding circuit, specifically the ball mill circuit, how well is it presenting coarse particles to the ball mill so that the ball mill can then grind them. If the ball mill is seeing a lot of already product-sized material passing down the length of the ball mill, that's going to generate overgrinding, and that overgrinding is going to consume power that's not being used very efficiently. So as much as possible, you want your classification system efficiency to be above about 70%. If you're greater than that, that's fine. If you're less than that, then you probably want to do something like rejig the geometry of the cyclone to give you a higher percent solids in the underflow. If you've got a lot of fine particles, that might be because there's too much water in the cyclone underflow. There's a couple of variations of the ball mill grinding efficiency. In the MacIver version of functional performance, you're measuring a value that doesn't have any particular meaning other than you can track it through time. I add an extra component to that, which is the 11B value, which then allows you to directly compare the kilowatt hours per ton of product produced by the ball mill in your industrial mill versus a laboratory mill. And you should be about 80% of the laboratory mill when you measure the industrial mill. So that's really useful. You can just measure it as a percentage and then compare to this threshold. Because you've separated these two efficiency metrics, this helps you identify which part of your circuit actually needs improvement. If the classification efficiency is fine, like 75%, don't spend your effort working around the cyclones. Focus your effort on the ball mill if the ball mill efficiency is 65%. SAG feed. You're going to want to grab a fresh feed sample. So this is plant feed, which is going to go into your SAG mill. You want about 200 kilos of this, so it's going to be a big drum or a big barrel. And it should be representative of the material that you are milling in the grinding circuit when you're collecting all of the samples around the wet part of the circuit. So for example, if you're collecting the feed sample from ahead of the SAG mill feed stockpile, you want to wait a few hours to do the survey in the grinding circuit so that the material you sampled on the feed belt gets time to pass through the stockpile and then arrive in the plant. You want that feed sample as much as possible to represent what's going through the plant when you're doing the rest of the survey. Once you've collected this sample, you're going to send it to a laboratory and you're going to do a series of laboratory tests. Most important tests are the bond ball mill work index test, and you want to run this at least 3 times at 3 different closing sizes. You want to measure what happens with the work index as the particle size changes by measuring 3 of these at 3 different P80s. You must take a JK drop weight test. This is the full drop weight test sample. And there are abbreviated tests out there that aren't the full JK test. I'm not recommending those for this survey. If you're going to do the survey, do the full test, not an abbreviated test. It's really a good idea to have a bond rod mill work index and a bond crushing work index. And the bond rod mill work index, this has to be done at a laboratory that has a proper wave liner on a bond type rod mill. The crushing work index rigs, there's a couple of variations out there. There's all sorts of drama around the bond crushing work index I won't get into, other than if it gives you a low number, that means something. If it gives you a high number, that means something. And if you run 2 different tests in 2 different labs, you're going to get different numbers, but they'll probably be both high or both low. That's all you need to know about that. These bond, rod mill, and crushing samples are necessary to run things like Barrett's equations or to do the specific energy consumption by the bond efficiency metric. If you don't have those, you're not going to be able to do the full suite of benchmarking you want to do for your circuit. And don't worry about the fact that we're doing a rod mill test in the lab and we're doing a SAG mill test in your plant. The methods that we use to benchmark take all of that into account. Right? Don't believe people who tell you that rod mills don't give you useful data for running SAG mills. On this SAG feed sample, you also want to grab the granulometry, and you want to go all the way down to whatever the cyclone P80 size is. So you want to know how much of the finished product is already in the plant feed. So if you're going to 104 micron in your grinding circuit, you want to know how much 104 micron is in the feed coming down the feed belt. If you haven't already got a moisture measurement for your ore, build that in here, because you're going to need to be able to work out what the dry tons per hour of feed coming down the feed belt is. So make sure there's a moisture measurement either here or you already have one and you have a good picture of what the moisture is in your ore. We're always dealing in dry tons per hour in these metrics and not wet tons per hour. Build some redundancy into your program. So one example of redundancy that improves the robustness and improves the value of the survey is each of these slurry samples, right? So the cyclone overflow, the cyclone underflow, these are slurry samples. So build in a sampling regime where you have alternating buckets for each sample. So you have, for the cyclone overflow, there'll be a bucket A and a bucket B. The first sample of the cyclone overflow goes into bucket A. Wait 10 minutes. Second sample goes into bucket B. Wait 10 minutes. Third sample goes into bucket A. Fourth sample after 10 minutes goes into bucket B. The idea here is you want to measure what the sampling uncertainty is in this measurement. Ideally, these 2 buckets should have the same characteristics within, pick a number, 5%, 8%. If they're wildly different, that's a good sign that this stream that you're sampling is not really under control, and that's one of the outcomes of the survey is how can we make this stream run more consistently? How do you get the variation out of whatever it is that's varying? It might be the flow or it might be the granulometry. This sampling in pairs like this allows you to actually calculate what the sampling uncertainty is of the stream. So that's a useful thing that you can add to your shopping list. Another thing that this redundancy gives you is if there's a problem and one of the buckets spills, you still have a bucket that represents that stream. You haven't lost everything in the case of a small disaster of somebody tips over a bucket. So redundancy, build that into the program so that little mistakes don't cost the whole program to fall down flat. Cyclone overflow and underflow, you must have proper sample cutters for these. They have to be the long wedge-shaped ones with a feed slot across the top of them. You cannot use a coffee cup mounted on a stick. That is not a proper sampler, and if you use something like that, you're going to get random numbers out of these samples. Use the proper samplers, look at that GMG guide, they tell you how to make those samples. Make sure that the length of that slot is long enough to pass all the way through the stream that you're trying to sample. Things to do. Do spend more time planning your sampling than actually pulling the samples. Do have enough trained people to collect all of the samples. Make sure nobody's rushed. Make sure there's no panic. Make sure people aren't forced to run up and down 3 stories worth of stairs every 10 minutes to grab a sample. Have enough people. Make sure they understand how to properly sample these streams. You don't want biased samples. People need to understand what the word biased sample means. Do have all of the buckets already labeled and already sitting out in the field before the survey. People should not be messing around with pens marking on a bucket when they're supposed to be taking the sample. Do check beforehand that all samples can be collected safely. Nobody should be in a position where they're at a fall risk. Nobody should be collecting a sample where you're dealing with a conveyor and you could potentially end up with that conveyor catching your sampler and hitting somebody on the side of the head with that sampler. Right? Safety must be built in before you start doing anything. Do coordinate with the mine to have a steady and homogeneous feed. One of the things that can cause a lot of uncertainty in a survey is ore variability, and you need to cut that down as much as you can. We're trying to measure how the plant is performing, not how variable your ore is. There's other ways of measuring ore variability. You don't want to use a plant survey to do that. So try and ask the mine to give you a consistent feed. You don't want the stockpile running empty. Ideally, the stockpile shape should never change. It shouldn't go from a cone to being inverted during your survey. That's going to potentially mess things up. Talk to the mine, and as much as possible, ask them to have a homogeneous and steady feed for your survey. Don'ts. Do not take shortcuts. Always work safely. Nobody needs to be injured to do a survey. It should never happen. Don't take shortcuts that bias the samples, right? If you have a cutter that is too small for that stream you're trying to cut, don't start the survey until you have a proper sampler. Don't collect bad data. Again, making sure samples aren't biased. I keep talking about this. There's only certain mathematical adjustments we can do after the samples are collected, and there is some bad data that we just can't clean out of the system, and it results in me giving you back an efficiency metric is, well, you're somewhere between 80% and 120% of where you should be. Now, if that 20% range is okay, then all right, fine. It would be better if I can say you are 90 to 95% of where you're supposed to be. Therefore, you have between 5 and 10% improvement you can get from your plant. Maybe more throughput, maybe a lower P80. So the better the data you collect, the less error bars, the less uncertainty range you're going to get back on your results. Don't mishandle the samples. Each bucket, make sure you identify it in duplicate, right? Bad things happen out on a plant floor, and sometimes you end up with a label gets rubbed off. Make sure there's a second label somewhere on that bucket. Avoid spillage. As soon as a sample is taken, put a lid on it and make sure that lid is secure. If the bucket tips over and you lose the sample, well, hopefully you've done the A and the B bucket thing so you're not completely lost, but it's even better to just get that sample secured beforehand and not spill anything. Because we're measuring percent solids on these, you also want to make sure that you don't have evaporation taking water out of the samples. You don't want to have people hosing, doing cleanup, putting water into the samples, right? don't mishandle the samples. Laboratory testing. There's going to be two types of laboratory testing done in your survey. You're going to be generating the granulometry and percent solids of particularly these slurry samples. And then you're going to be doing ore hardness testing on that plant feed sample. So that's the big 200 kilo sample that's going to be in a couple of drums. The two types of tests, they can be performed at separate laboratories. So you can do the sieving and the granulometry and the percent solids measurements in your met lab. You're probably going to have to send out to a specialized lab the ore hardness testing. Not every mine is going to have a JK drop weight rig and a bond ball mill rig and a bond rod mill rig and a bond crushing rig. So you're probably going to need to send some of those samples out for specialized testing. You can do other things at the same time, right, that aren't necessarily related to the grinding. You could measure the geochemical nature if you're trying to match this survey back to ore characteristics. It's a really good idea to ask a geologist to come and look at the ore you've collected off the feed belt. Let them tell you what you've actually collected. Things like that. The full laboratory test reports should be provided to you. So this, in the bond tumbling test, this means not you get one line that has the P80, the F80, and the grams per revolution along with the work index. You want to see the per cycle information. So how many grams per revolution in the first cycle, the second cycle, the third cycle. You want to see the full particle size distribution as a table for the feed and for the product. Right? So somebody like me, I can go into that feed data, the feed size distribution, and I can suss out other information from that. The JK drop weight test, the key thing you want to get out of that test is not just the A and the B. You also want to look at the graph of the T10 versus the ECS. Now there are ways to interpret that table I won't get into here. Another thing to know about with the JK drop weight test is it should be highlighted where there is synthetic data, if there is any in your test results. Sometimes in the interpretation of the JK drop weight test, the licensing authority will inject synthetic data where things weren't measured in the lab or where things that are coming from the lab look a little wonky. So that's fine if there is synthetic data in there, but it needs to be identified and it needs to be disclosed. So the bond ball mill test P80, you need to run the multiple bond ball mill tests for this reason. Ball mill work index changes as a function of size. And every ore has its own characteristic change to work index in size. The grams per revolution, that changes per the screen size that you're running the test at. So when you're doing things like the functional performance, we need a very accurate gram per revolution measurement to work into the functional performance equations. We need to be able to generate this chart for your ore, and the only way we can do that is if you take 3 or more of the ball mill tests at these different sizes, and we can interpolate between your test data to get the correct work index and the correct grams per revolution to do these measurements. So the power draw in the mill. How much power is being drawn? We're probably going to take that from your plant DCS system. So this would be a PI system or a data librarian. One of the questions usually comes out is how much power can be drawn from the mill. That I'm not going to deal with in this survey. There are more complicated surveys where we can deal with that question. But we should look at whether the power is being measured in the proper place in this survey. One of the things to know, what is that DCS power indication? In a lot of the older plants, in a lot of the simpler plants, what you're looking at is the electrical power going into the motor. Right? Electrical power is an easy thing to measure, so often there'll be a couple of transformers in the electrical network, one measuring current and the other measuring the voltage, and then that will output what the power is electrically at the measurement point of the voltage in the network. And usually that voltage measurement is just ahead of the mill motor leads. So what you're measuring is the input electrical power to the motor. What the Bond equation and what the Morel-MI equations and what the functional performance equations are all tuned to is the mechanical power absorbed by the mill. So it's the power at the shell of the mill or the power at the pinion of the mill, but it's mechanical power, it's not electrical power. So if you have an old plant, you need to generate the conversion for the motor efficiency and possibly the mechanical efficiency if there's gearboxes and things like that. That's beyond the scope of this video, but that must be done. Also know that if you have a gearless drive, your power measurements are already mechanical power, and they are mechanical power at the shell of the mill. You don't need to do any electrical or mechanical efficiency changes. There are certain new mills that have gear-driven mills with sophisticated control systems. So ABB, for example, their ACS 6000 series, gives you a signal to the control system which is corrected to be the mechanical power at the output shaft of the motor. And that mechanical power, you don't apply an efficiency for the electrical to mechanical conversion of that. The control system's already done that. You might need to put a gearbox or a gear efficiency on it for any mechanical losses downstream of the motor. But certain newer applications with the more sophisticated control systems, you might already be getting mechanical power. So in conclusion, a ball mill survey, it is a health check for your grinding circuit. If it tells you that your circuit is running efficiently and that there's no big issues, great, you're done. Your metallurgical people can go to the float plant, they can go to the tailings thickener, they can spend their time dealing with the other parts of the plant that need labor, need improvement more than the grinding circuit, because you've measured the grinding circuit, it's doing fine. Otherwise, it will the survey will identify where do you have opportunities for improvement. If you have the ball mill has balls that are too small in diameter for what's going into the ball mill, that will show up in things like functional performance. And then using like selection functions, you can even identify which size class the ball mill is most efficient at grinding, and then you can compare that to the actual sizes of particles going into the ball mill. So these sorts of mismatches can tell you where you can improve your circuit through things like changing your ball diameter in one example. Always plan carefully, execute safely, and build quality control and redundancy into your survey and into the laboratory program. We want the most robust data that we can generate to give you answers that have the least amount of uncertainty on them as possible. Poor quality data gives us low robustness in our calculations, and it's going to give a lot of uncertainty on our conclusions because there's just too much noise in the data if samples weren't collected properly, if you have samplers that are inappropriate, and these sorts of things. So have a good survey, and we will see you in the next video. Thank you very much for watching, everybody, and we'll see you then. Bye-bye.